Hello everyone, my name is Felipe Guajardo, this is Alex George, David Ducazi, our team is DAF Motors, and today we are going to be talking to you about the race engine optimization project. Before I go more to depth into our project, I would like to talk to you about the organization we are working with, SAE, the Society of Automotive Engineers. The SAE group at FIU competes in the Formula SAE competition, where students are tasked to build an open-wheel Formula-style race car. We are configuring our engine for optimal performance under the conditions allowed by the competition rules. Some of those limitations are the engine displacement cannot be more than 610 cc. All air intake has to go through a 20 millimeter restrictor, and finally we'll be using 100 octane fuel. Because this is an international competition, we're going to be translating our reports into various languages, as well as converting the units to both systems, and finally using as many nonverbal simulations as possible.
Now, our project is focused around the compression ratio of our engine. The compression ratio of an engine is the volume of one of the cylinders at the bottom dead center divided by the volume of the cylinder at the top dead center portion of the stroke. And it is important because the compression ratio of an Otto cycle engine is fundamentally related to its thermodynamic efficiency. The higher your compression ratio, the higher your efficiency, and the more of your fuel becomes power and the less becomes waste heat. The reason we're focusing on this attribute is that at the competition we're going to be allowed to use 100 octane racing fuel. And this fuel will tolerate a higher compression ratio as compared to the more commercially available fuels before going into pre-ignition or detonation that could potentially damage any internal engine components. This arrangement leaves the potential on the table for increased power and fuel economy as compared to the unmodified engines that most teams go to competition with. Now, in a moment, I'm going to tell you about our design, but first I want to tell you a little about how we got there. Behind me, you'll see a few of the different alternative designs that we discarded earlier on in the process. We had initially considered milling down the surface of our cylinder head to increase power and compression ratio, but we found that our potential gains from this process were somewhat limited. We also considered changing out our camshaft with a custom design that would bring our power band down into a more accessible RPM range for the competition. We also found that our gains by this method were somewhat limited. We finally settled on offset grinding our crankshaft to increase the length of the stroke, but we found that this method was unnecessary once we decided that our donor vehicle was going to be a Honda CB550. So what we plan to do with that Honda CB550 engine is we're going to take out its crankshaft and switch it with a crankshaft from a larger displacement engine of the same engine family that will fit. This is going to increase its stroke, bringing our displacement up to right underneath that 610 cc displacement limit that you just heard about, and also bring our compression ratio up. From there, we have to respec all of the internal components of the engine to actually bring our compression ratio down a little bit because that first modification was a little too high. And also to maintain all of the important internal clearances so that we don't bend any valves or damage any other components when we actually run the engine.
So I'd like to take a moment and go over some of the logistics behind our project. Behind me, you'll see our timeline and with all of our major tasks. Now, as Alex just mentioned, we've already done our motor selection. We've chosen the Honda CB550. We've chosen the CB550 for several reasons, among which are that it's easily modifiable. There's several aftermarket parts available, which are also easily interchangeable, and it's cost effective. Now, I'd like to also take a moment and go over some of the tasks both behind us and still ahead of us. As you see, all of our research is done, but our motor acquisition, dynametering, and modification process are all still ahead of us. Now, also you'll know that the dynametering and the modification process overlap, and that's because we'd like to dyno the motor after each individual step, so we can actually quantify our gains from each individual process we do. Now behind me you'll see our cost analysis, and as of right now our project is primarily funded out of pocket. But with the help of SAE, we've been going out and looking for both funding through sponsorships and any help we can get through partnerships. And through SAE, we've created a partnership with the Creative Workshop, a workshop that primarily modifies and restores older vehicles. This is useful to us because they've actually just purchased a dynameter, it's brand new, and they've offered to let us use that dynameter free of charge, which is a good savings of $500 for us, which represents a significant cost reduction in our project cost. And that's important as we move forward towards our goal of providing a functional prototype for not only for our SAE team, but more importantly, for providing a useful body of knowledge, not only for our SAE team, but for SAE teams around the world. Questions?
Okay, so I understand more what you're working on is changing the length of your stroke.
We're focusing on raising the compression ratio, and like Alex mentioned, we have several methods of doing that. In this case, yes, we're changing the stroke to effectively increase the compression ratio.
Change the stroke, shorten the rod, or possibly thicken the head gasket to back off the compression ratio. But that first modification will put us at 16 to 1, which is too high even for 100 octane fuel.
Okay. Have you thought about, besides just doing that, I mean, do you have access to a flow bench?
As of right now, we don't. Like I said, we're still looking for partnerships and creative workshop.
Actually, I have a friend of a friend who has a flow bench I may have been able to use. But in this particular case, we have to use 20mm restrictors. So anything we do with increasing flow is kind of subject to a lot of diminishing returns.
Right.
That's one of the reasons, similarly, we didn't consider forced induction because you're just expending more and more power to force a mixture through a small hole.
The reason I ask that because I'm very aware of your competition. I know exactly what you guys are doing. So you got to balance not only the compression ratio, but you also have to look at how to increase the airflow going into and out of the cylinder head. You know, that's where you get your power, and also optimize your fuel you're using. So I understand your limited time and you're working on this part of the project, but as a team as a whole, you should consider saying, okay, we need to look at the cylinder head also, maybe a different group of guys, you know. So it's an expensive task that you guys are doing. The whole car is an expensive vehicle, and go for that funding. You know, I know you guys have been doing that. I know Alex, he's in charge. Is he still in charge of the funding?
Alexis, or?
Alexis,
yes.
Yeah. So funding is probably one of the crucial things for this competition. And the track, have you ever been out to the track?
Unfortunately, we haven't, but we're working with Alexis and the other SAE members, and they're kind of helping us and giving us pointers, and whenever we need information, they've always been more than ready to help us out.
Okay.
At the outset of design, we had actually hoped to get some funding from SAE, but right around the time we were starting, SAE lost some funding, and so we lost some funding.
GM, Ford, Dodge, Chrysler, BMW, Navy, Caterpillar, they all sponsor these events. Boeing, go for these big companies, they all do this.
Actually, yeah, I heard, I'm not sure if it was you or one of the other gentlemen that mentioned looking at, you know, not just looking at local places, but big companies, you know, be ambitious with it.
Right.
And that was definitely one of the things that I was considering, as you guys mentioned, definitely going out and hitting up the major companies and saying, hey, you know, we're working on this competition. You know, is there something you can do? And one of the things that one of you guys mentioned that I also liked was that a lot of these companies not only help with funding, but can actually help with parts. And that since we haven't actually done we haven't gotten the motor or any of the parts that we're going to be using yet, that would definitely be something that could help us out, and something we're definitely going to look into.
Okay. I'm done with questions. Sorry.
Okay, the question path I wanted to go after is, you're spending a lot of money developing a motor. Do you have any simulation on the front end of this that will assure that the decisions that you've made on these expensive components are the right answers?
Yeah. Well, we have some very rough simulations at this point. We can't do detailed simulations at the very front end because we don't have the detailed specifications of the engine we intend to use. Once we buy the engine and take some more detailed internal measurements, say quench specifications and various other combustion chamber properties, we intend to do some more computerized, maybe finite elements.
Okay, so we expect to see that with this work. Second piece of that is that on the testing side, are you going to set up some kind of a planned testing pathway so that you do something to learn something that you make your adaptations and adjustments to, or is this just going to be a one-shot?
No, actually, that was one of the things I was mentioning with the timeline. We wanted, as we make each individual change, I mean, obviously, or each functional change that we can test, We want to dyno as often as possible, especially now that we have the partnership with the Creative Workshop, and they gave us free dyno time. We can go in there and test as much as we want for as long as we want. So we want to take that opportunity and test as often as we can, so that we can learn what each individual step gives us.
Okay, so I have definite interest when you write the report on this, for me to see iterative development through this with lessons learned on the way, so that we understand that you're actually using the tools.
We're actually very excited about the opportunity to get the free dyno time, because it means that we can dyno over and over and over as we keep changing things without incurring too many costs. As far as writing an actual test method, we haven't done that yet, although it's something that's been on my to-do list. I used to work for a pharmaceutical company in the QC department. I used to write test protocols. So I'm really confident I can handle that.
Okay.
I got 3 questions. As one of my colleagues said, you need to go looking for funding all over. Go global with that. So you say you're using a Honda Civic engine?
No, it's not the CB550. It's a motorcycle.
Oh, okay. Well, go back to Honda. Talk to them. They might be interested. Okay. That's one question. The other question is, you're using 100 octane. I'm concerned about the cost and availability of that, and whether or not, when you really down the line, whether or not you might not have to use a lower octane.
Well, the SAE distributes a document with the rules, and in it I'm pretty sure they promised to have 100 octane provided at the competition itself. As far as getting it for our testing purposes, you can drive down to Homestead Speedway and buy racing fuel. Otherwise, there are various companies around the world, such as like Rocket Brand Racing Fuel, will ship you with drum if you really want them to.
At what cost?
It's like $9, $10 a gallon. It's expensive, but we don't need very much of it. It's insignificant to most of the rest of our cost.
Right. And since our motor is primarily for the SAE competition, and that's why we use the 100 octane fuel, which is actually a focal point of our project. That's what they're providing. As for maybe using this in other scenarios outside of the SAE competition, then this would have to be adapted for other readily available fuels. But a big thing about the SAE competition is that it's actually for racing enthusiasts, car enthusiasts. So a lot of these guys are going to want to be able to get as much as they can, and they'll order that drum of 100 octane fuel because that's what they're doing. They're trying to race. They're going for that performance.
Okay, my final question is, I've been looking at your report, and it's an edited report that you posted. So I have a concern with that, but more importantly, we are working with the APA style guide for reporting, and it looks like you're using either Chicago or MLA. Is there some reason for that?
The formatting for the report was we've had some issues with clarifications, and it was an oversight for we used MLA rather than AMA.
As far as
APA, sorry. And as far as the report being,
we were not aware that the website we had to upload the report to would convert to PDF and open all those changes up to. We're going to copy those right away.
Okay.
No, you can't use E85 fuel. That's like 100 octane as well.
You can use E85 fuel, which by some estimates is higher than 100 octane.
105. So.
They specify a smaller diameter restrictor plate for the use of E85, and I feel it's probably more effective to go with gasoline in this case. There's a larger body knowledge available.
So they do change the rules if you're using E85, or is
Yeah,
it?
in earlier versions of the rules, I think they used the same restrictor plate, and I remember reading that and thinking, well, someone's going to really exploit that, and I bet they did.
That's why they changed the rules.
Just a thought, because you said your limit is the size of your orifice. You're allowed to have a maximum. There's nothing to say you can go a little bit less. Yes, you are restricting the engine, but if you put a supercharger or turbo on, I know you can't use nitrous in there, but you're kind of compensating that restriction, to get more air in there. But that way, if you have to change fuels for whatever reason, your restriction allows you to do it.
Actually, I'm glad you brought that up, and I wanted to touch on this with the last question as well. We wanted to have a project that we were sure we could do, which is why we focused on compression ratio above anything else. We are ambitious with our goals, And we would rather shoot above that, like you said before, with the restrictor, fuel injection, putting a turbo on there. There are other things that and changing the pistons, there are other things that we would like to do, but we were concerned with the time and our knowledge. We weren't sure at the start of this how much we were able to accomplish. So I'd rather go in and have this presentation and have this set as our goal, and then go over those expectations rather than to be too ambitious and then fall below. But those are definitely things that we're looking at with the SAE group.
Quick question there. So you found it a better option to increase the stroke as opposed to increase the bore?
Yes. We chose to increase the stroke. A large portion of the design was that, well, okay, you can increase displacement two ways. You can increase bore and you can increase stroke. Increasing the bore will increase your displacement, but it won't do anything to increase our compression ratio.
Right.
Increasing the stroke, on the other hand, does, which is why we're focusing on it. Our primary objective is actually to increase the compression ratio. The displacement is just incidental. We'll get our science we can.
Okay, thank you for the
Okay.